Okay, dear students, welcome back to our lecture. We go on with the second part of what we did, and I would like to start off with a little example. Let me see where we are. Here's with a little example just to strengthen the idea of what we're doing with turbulent flows, just to fix this concept a bit of having a critical Reynolds number. Can you see my slide right now? I hope. Maybe let me just make sure it's the right version. Yeah, that one. Okay, now you should have the right. So a very good example of what's going on in a more mathematical sense. I mean, last hour we've mostly looked at turbulence in a qualitative sense. A very good, maybe the easiest example of showing what's going on in a mathematical sense is the so-called Lorentz system. It goes back to an atmospheric physicist called Lorentz, who developed this system in 1963. He was actually trying to create a very simple system of equations, three equations, ordinary differential equations, which model the convection process, convection of warm air rising up and cooling down, and another air coming down. And what he ended up with are the three equations you see here in this box. The variables are now x, y, z, but in theory, or originally when Lorentz developed that, I think one was temperature, one was velocity, and the third one was, I don't know, pressure. So we had multiple variables, which we now call x, y, z. So just consider this to be an abstract system of variables, something like a simplified model of what Navier-Stokes could. And what is really special about these equations are these terms here, the xz term and the xy term. Why are they special? Because they are nonlinear terms. If the system was a linear equation, so there's no nonlinearities, no products of variables in it, the system would be rather boring. We would not see all that much. But what we're going to see now, and maybe you have seen it somewhere on the TV, this Lorentz attractor you have on the bottom right of this slide, this is only there because we have these nonlinearities in the system, just as we have nonlinearities in the Navier-Stokes. And just as in the Navier-Stokes equations, where we have the Reynolds number, which is telling us something about the weight between viscosity and the nonlinear term, we have here another number. It's called the Rayleigh number, Ra, the Rayleigh number, which in that system plays a similar role as the Reynolds. Rayleigh number is it's a slightly different non-dimensional number used by atmospheric scientists. Okay, but let me just make a few examples. I've written a little Python script, which I actually uploaded on Elias, that you can also play with it. And let me switch the screen here so that you can see the Python script. Yeah, here it is. And well, I'm not sure if it's large enough so you can see it, but what we have here on the left, the two lines that are highlighted, this is actually where I can set the Rayleigh number. So just as I could set a Reynolds number. And the Rayleigh number currently is set to 10. And I also have to set some initial conditions since we'll be solving these equations. And as initial conditions, I actually choose a point x1, which has 3 coordinates. The x coordinate is minus 0.1, the y coordinate is minus 0.1, and the z coordinate is minus 0. So it's a point in space, x, y, z. The three variables, x, y, z, are understood as coordinates in space. I'm also setting a second point, the second starting point, so we have actually 2 points which developed. and that point is actually almost the same location, also minus 0, 1, but here it's a plus 0, 1, and the z coordinate is also a plus 0. So 2 points at different x, y, z locations, and then we let the little Python code integrate or solve that system of equations and see where these points are moving. Let me just start that. And what you should see in a second, yes, here are these 2 points here. So blue is one of the two. I think blue is the x2 and red is the x1. And you see how they're developing and they're starting to move. And they're actually, well, I think the trajectory of these points is not very interesting. They're going like in spirals. And actually spirals get smaller and smaller and smaller and smaller, and they will eventually end up or converge each toward its own equilibrium point. Actually, now you can barely see anything moving anymore. So we have started off with 2 points, and both of them started going to a spiral and ended up at the fixed point. Such points in space, such points x, y, z, are called attractors, because they attract any solution to go toward that point. An attractor, especially if it's a stable attractor, is attracting all points. And you all know what a stable attractor looks like. Let me just quickly go back to the blackboard. The typical very typical situation you will all know is if you have a surface of that shape and you have a little bead and you place it here and you let it go, and of course it will fall down or roll down, and maybe it will swing a bit about the lowest point, but eventually it will end up down here at the lowest point. And if you start off with the bead somewhere else, maybe at this point, it will also go to this stable point. So this location here is a stable attractor, or just an attractor. And the situation we've seen before was actually there's a second well here, and we had a blue point, and the blue point fell into this hole, to this stable attractor, and we had the red point, and it fell into this hole, into this stable attractor. So the example we just saw, we have 2 stable attractors, one here, one there, and both points fell into this location. This is pretty much what we have in a laminar flow. There's a rather stable attractor. Laminar flow is an attractive situation, and the flow is stable about this situation. Let me go back to the main screen. And let me increase, oh no, let me actually do something else first. Let's blank out these lines here. Let's first stop here. Yeah. Okay. That one blanked out, and we take slightly different starting points. Just look at where the starting points are. They're almost at the same location, right? We always start at the same point, just the perturbation like by 0.1%. And if we start that, well, the result is not so surprising. What happens is that we actually don't even see both points anymore. We actually just see one point. But the 2 points are on top of each other. So in our situation here, we were to start at almost the same location. Okay, so we take these starting points, which looked rather boring in this case now, and we're going to start them again. But this time we keep these starting points, but we increase the Rayleigh number. So we increase the Rayleigh number to 28. There's some hindsight why I choose this number. So we go to a higher Rayleigh number, something like a higher Reynolds number. Let's see what happens. So again, we start off where both points are on top of each other. We cannot really make out the blue and the red point. We actually just see the red point, which is on top of the blue one. Again, it goes into a spiral mode, but the spiral is not getting smaller and smaller. It's actually getting bigger and bigger. And now the point all of a sudden seems to create a second orbit. Oh, and there's now the blue point. So both points were very close together and were actually almost overlapping, but after, well, actually an unpredictable number of spins, it just starts again. The two trajectories all of a sudden split. Let's look at it again. We're spinning. The circle, the spiral is not an inward spiral, it's actually a spiral that gets bigger. The two trajectories are still on top of each other. Still orbiting, creates a second orbit, comes back. And I think very soon they're gonna split. Yeah, here they split. One stays on one side, and I think the blue then switches over to the other side. At one point, where is it? Yeah, now, okay, the blue goes back there. So it's a really uncontrolled way, and that's exactly what happens in turbulence. If we increase our Reynolds number, or in that case, the Rayleigh number, beyond a certain point, all of a sudden, even the smallest difference in the initial condition, maybe in the beginning everything moves the same, but all of a sudden they split up, and each part does something completely chaotic, unpredictable in such a situation. And by the way, this shape that is formed now is not a stable attractor, it's called a strange attractor in chaos theory. So this just is a little mathematical visualization of what is happening in such a nonlinear equation. Share my slides again. There we go. Yeah, so that was the Lorentz attractor. Now we should actually move more into a mathematical description of actual turbulence, not just the example of Lorentz. And to this end, we need to introduce a little bit of statistics here. And we need to introduce a concept which is again named after Reynolds. It's not the Reynolds number now, it's the Reynolds decomposition. And what does it mean, the Reynolds decomposition? Well, if we do have a turbulent flow, and let's say we have a very good experiment where we can measure velocities at a certain point very accurately in time, and we were to measure what this velocity is doing, we would see that it's fluctuating a lot, right? Because of these small scale eddies that are present. And if we ran the experiment again, it would oscillate again, but because the initial conditions are slightly different, the oscillations would not look exactly the same. Let me maybe draw something on the blackboard again, just to show you a little bit of what such a measurement could look like. Go to this side, blackboard. Let's say we do measure a velocity u over time. And because it's turbulent, the velocity will fluctuate. This may be the signal that we're getting. The next time we run the same experiment, the same measurement, but the measurement will look different because it's unpredictable and chaotic. And we do a third experiment, and so on. And each time we have different results. But with the bare eye from looking at this, you probably recognize the structure. You see that there's some kind of development which looks the same, a mean development. So wouldn't it be nice if we can describe a mean velocity u, capital U now, not lowercase u. Let's call this the measurement u tilde. U tilde is like what we have measured for every instance of an experiment. The next experiment can be the same, different. There's a mean, and the difference between the mean and the actual measurement is a fluctuation, u. So we will call or decompose our measurement u tilde into a mean flow plus fluctuations. Mean and fluctuation. And actually the amplitude of these fluctuations gives us a measure for the intensity of the turbulence. And the mean flow gives us an understanding of, well, what the mean flow is doing, what the flow overall is doing, plus the turbulent fluctuations. So how can we go about this in a mathematical sense? Well, running many experiments, the same experiment many times, many instances of an experiment, and taking a mean is something called an ensemble average. We're averaging over multiple experiments. And this is what is shown in the slide here. The ensemble average is the sum of all instances of the experiment divided by the number of experiments. Like we do 100 experiments, and then we average all the measurements at a certain time over 100 different measurements. And then we obtain a mean flow. Typically, we denote the ensemble average by an over bar. So U bar denotes the ensemble average, which we then call capital U. And this decomposition into a mean component and a fluctuating component is called the Reynolds decomposition. Now, what can we do with it? Well, there's one interesting and technically extremely important thing, and many of you will come across that, and that's called the Reynolds averaged Navier-Stokes equation. So what you can do is you can actually modify the Navier-Stokes equations in a way that they're written not in the variable u tilde, right, in the variable of the actual turbulent fluctuation, of the actual turbulent flow, but that it's written in function of the mean flow. So how do you do that? You take the full Navier-Stokes equations. We're not going to do this now, I'm just explaining to you. You take the whole Navier-Stokes equation, and wherever you have the original u, or here u tilde, you replace it by u, capital U, mean flow plus fluctuation, right? There's no magic behind that. You just replace variables. And then you multiply that out, or you write that out, you split the terms wherever you can, and then you average the whole equation, left-hand side, right-hand side, you average it in an ensemble average sense. All the terms which have only the fluctuation u in it, if you average a fluctuation, by definition, it will be zero. So all these terms will drop out. And if you average a mean quantity, it will again be the mean, right? That's also by definition. The average of the mean is still the mean. So you end up with an equation which then almost only, I'll come back to that, almost only contains the capital U's. And that's called the Reynolds averaged Navier-Stokes equation. And that's what it looks like, the boxed equation. And see, in this equation, except for the red part, which we'll come back to in a second, except for the red part, it looks almost identical to the original Navier-Stokes equation. We have a du dt, we have a dp dx, now a capital P, the Reynolds average or the ensemble average pressure. We have a viscous term on the right-hand side. And we even have a nonlinear term on the left-hand side, all written in capital U. The only difference in the Reynolds average Navier-Stokes equation is that we have this red term. And again, this comes out of this nonlinear term, because if you have this nonlinearity and you have a U, capital U plus lowercase u times capital U plus lowercase u, you have these, when you have a square, you get these mixed terms, and you end up with a term which has ui, uj, these are the different velocity components, so uv and w, ui, uj averaged. And that's a term we actually do not know beforehand. Right? This is what is called an unclosed term. If this red term was not there, we would have an equation where we have only the mean quantities in it, and we can try to solve it just as we solve any other Navier-Stokes equation, and we just get a solution for the mean flow without the fluctuations, which for many technical purposes is good enough. The problem is that this red term is an unknown quantity. Statistically speaking, we can try to understand what this term ui, uj over bar means. It actually is a covariance. So for ui, uj, when I and j are the same number, like u1, u1, then it's actually a variance, right? You have u squared and you take the average over it. That's how you compute the variance of a statistical quantity. If you have u times v over bar, that's the covariance of u and v, uw and so on. So this is a covariance term. This tells us how a fluctuation in u is correlated to a fluctuation in v and w. So it's an inherent characteristic of a turbulent flow. It has a name, and surprise, surprise, it's named after Reynolds. It's called the Reynolds shear stress tensor. This covariance of the fluctuation velocities times rho, and there's a minus sign for historical reasons, is called the Reynolds stress tensor. You can analyze this term, and many people have done this for decades and still are doing this for maybe their whole career. It's very important to understand what this term is, and we still don't understand what it is. So you can start analyzing it, and one of the first things you find is that this term here, at least the off-diagonal terms, the covariances will typically have a negative sign. And this is explained on the picture on the right-hand side. You have here a flow, a mean flow, a shear flow, which is a bit faster higher up and a bit slower lower down. So something like you might have in the boundary layer. And you have a little fluid packet in the middle. And just assume now that you have a turbulent fluctuation which is positive in v, in the v velocity. So it's pushing it up. So that turbulent fluctuation is pushing it up. If this packet is pushed up from here to this location, you will generate a velocity deficit, that the packet will be slower than the mean flow. So with respect to the mean flow, this will be seen as a negative change in the u velocity. So positive V fluctuation creates a negative U fluctuation. This is why positive V is correlated with a negative negative U. So the covariance is negative. And the opposite is also true. If V is negative, this will lead to a positive U. So typically, this tensor is negative, and if you check all these signs, you can see that it can also, at least in theory, bring it to the right-hand side of the Reynolds average Navier-Stokes equation, and then it has the character similar to an additional viscous dissipation. So what this term is actually doing, it's representing the additional dissipation of energy due to turbulent fluctuations. The covariance of U and V fluctuations leads to an additional energy dissipation. This is exactly the term that is typically modeled in CFD codes. In CFD codes, the model for this term is called the turbulence model. So we'll come back to that when we have this lecture on CFD. But what you have in these codes, you can usually click which turbulence model you want. So different people along the decades of research have developed different models for this term, and you can now use these models, and depending on which flow application you have, some models are better than others. But they all are trying to model this single term here, and they're all helping to dissipate energy from the mean. There's a more mathematical way to understand that, and it now becomes a bit ugly on the slide, but let me just give you the idea of what has been done. So you can define an energy, something like a kinetic energy, for the mean flow. So it's 1/2 capital U squared summed over all velocity directions. So it's really like a kinetic energy if you multiply it by rho. And you can do the same for the velocity fluctuations, right? You can sum up the square of all velocity fluctuations and you get the turbulent kinetic energy. So lowercase c is turbulent kinetic energy. Uppercase E is a term for the mean kinetic energy. And you can again modify the Navier-Stokes equations such that you get equations which describe the evolution of this E, capital E, and the lowercase c. And these are the equations written down here. So two equations, one for the mean energy and one for the turbulent energy. And when you analyze the different terms, you see there's a bunch of rather complex terms, which, well, they do what they need to do, and some is transport, some is viscosity. But the important two, I highlighted with a blue box there at the end. And these two terms look identical. And when you look at them, you see again here this covariance, which we called before the Reynolds stress tensor, which happens to be typically negative for a positive shear rate of the mean flow. So this is a negative term here. So it means this term here, it will drain energy from the mean flow. And because you have exactly the same term on the turbulent kinetic energy, but with an opposite sign, it means whatever is drained here from the mean flow, it's added to the turbulent flow. And this is a very, very important concept to understand turbulence. In turbulence, the larger scale structures, the mean structures, they always transfer their energy toward the smaller, the turbulent, the fluctuating scales. Energy transfer from mean to turbulent flow, a very classical concept of turbulence. And if we follow this thought, and now it becomes you can fill a complete course on that, we come into the theory of Kolmogorov. And Kolmogorov was a physicist, I believe a Russian physicist, who tried to understand what this energy transfer from mean structures to turbulent structures mean, and how this large-scale energy can eventually dissipate in these smaller eddies. And he wanted to find out, is there something like a smallest possible eddy? And he ended up with something which is nowadays known as the Kolmogorov length scale, described by ETA. And I quickly want to show you on the blackboard the basic concept of that and some beautiful applications of that. So let me switch back to the blackboard. Give you the idea of the Kolmogorov scale. Maybe go to the other side of the blackboard again. So the idea was there must be a balance between energy coming in from the large scale and going into the small scales. So balance between input from large scales and the dissipation at the smaller scale. So the smaller an eddy is, the more viscous losses you have. Huh? The smaller an eddy is, the higher the shear rates, the more the viscous shear stresses. Dissipation at small scales. Right? So he had a process he didn't understand in detail, but he knew there's something large energy coming in, and there's something very small which drains this energy. And what he did was actually a dimensional analysis, bucking and pi. And he listed the variables that he had, the physical quantities to look at. So he defined a variable eta, which is the size of the smallest vortical structure in the turbulence. Unit m meters. Yeah, the viscosity, unit square meter divided by second. And the third thing, and that's the energy input from the outside, is how much energy overall is dissipated. And he called this the energy dissipation rate. Yeah, energy dissipation rate. And that's actually watt per kilogram. And if you carefully look at the units, watt per kilogram can also be written as square meter per second square meter per second to the third power. Maybe write this. So that's the 3, second to the third power. And I don't want to go through all the steps of bucking and pi, but essentially we have 2-dimensional units, seconds, and meters. We have 3 variables, so we end up with only 1-dimensionless group. One non-dimensional group. The only way to create something non-dimensional out of this is by multiplying eta by E divided by nu to the third power and everything to the 1/4. You can check that. This is a non-dimensional quantity. So this is some kind of a constant, a non-dimensional constant. And he actually wrote that out, and he said, my Kolmogorov length scale is given by nu to the third power divided by the dissipation rate to the 1/4. And that's how he came about with his Kolmogorov length scale. There were a few more steps involved, but in a nutshell, this is how it's been done. You can also extend this analysis. You can also come up with a velocity at the smaller scale. So how fast are these small scale vortices rotating? And what you actually obtain is you get a nu times epsilon to the 1/4. And if you take the scale and the velocity, so it is a length and the velocity, and you define a Reynolds number, a Kolmogorov Reynolds number, the Reynolds number of the smallest scales in the turbulent flow. So you would take the Kolmogorov length scale times Kolmogorov velocity and divide it by nu. And if you do all that, you will find out that the Kolmogorov Reynolds number is just 1, which tells us that the Reynolds number at the smallest scale is 1. So this is really where viscosity starts to dominate. This is why these vortices, they're very, very dissipative. This is where energy is dissipated into. And there's not really anything smaller than that, because anything smaller than that has dissipated before it can get smaller. So this is pretty much the end. This is the smallest scales that we can find in turbulent flow. And we can do a little example of that. We can compute what such a typical small scale will look like, or what it is. And the example I would like to make, let me move back here to this side to do that. Let's take the example of a blender. Blender, you know, these things where you can mix a smoothie or whatever. So an example. We have a blender, and we have a blender with 100 watt. 100 watts of power. And we assume that in this blender, when it's mixing, in this mixing process, it generates turbulence, and all the energy that it puts in, all the 100 watt, are eventually dissipated into heat through turbulent dissipation. Let's further assume that we pour into this blender 1 kilogram of water, or let's say something with a watery quality. Well, probably you don't want to blend water, but something similar. And the viscosity of that is 10 to the minus 6 meters squared per second. That's the viscosity of water. Okay. So, what is our dissipation rate? So we have 1 watt per kilogram. So we have 100 watt per kilogram, or 100 meters squared per second to the third power. And eta the smallest scale eddy is, according to our formula we have on the slide or the blackboard, is nu to the third power. Maybe I'll just turn over. Nu to the third power. So nu is 10 to the minus 6. 10 to the minus 6 times 3. That's nu to the third power. Divided by epsilon. That is 10 to the 2. And all of this to the 1/4. And that will be then at the unit of meters. Huh? How much is that? Well, 10 to the minus 6 times 3, that's 10 to the minus 18, divided by 10 to the 2, that is 10 to the minus 20, 10 to the minus 20 divided by 4, that's 10 to the minus 5 meters. Huh? Or actually 0.01 millimeter. Okay, so next time when you're blending something, look at it. Well, probably you won't see it, but the smallest scales eddies you generate with your blender have a size of approximately 1/100th of a millimeter. Smaller than that, structures will not exist because they will have dissipated before that. Everything will have dissipated. Let's switch back to the slides. So this is what Kolmogorov tells us. And if we piece all of this together, this transfer of energy from large to small, whole Kolmogorov theory, we do get something which is known as the turbulent energy cascade. And this is essentially a power spectrum of a turbulent flow. So you take a turbulent flow and you do a Fourier transform. And you measure how much kinetic energy is in a large scale structure, so like a large vortex, and how much energy is in the smaller scales. Here, where it's a 1, this is a wave number scaled with the Kolmogorov scale. So here on the right-hand side, this is the energy of the Kolmogorov scales, of the smallest eddies. So they have very little energy in it. This is where everything is drained and then dissipated. Here on the left-hand side, we have very small wave numbers, so very large structures. So maybe that's the biggest eddy you have in a boundary layer. And that carries a lot of energy because that's really moving a lot of fluid. It doesn't really dissipate a lot of energy here, but it's moving a lot of fluid. So this has a lot of energy, and every large eddy is moving, is transferring its energy to the next smaller eddy, that one to the next smaller, and so on. And the smaller as the eddies become, the more they're dissipating. So we have this cascade, the turbulent energy cascade, which is transporting large-scale energy to smaller and smaller and smaller scales until we end up at the Kolmogorov scale where everything is dissipated. There's some structure to this energy cascade. There's this range which typically decays with k to the minus 5/3. That's called a Kolmogorov's inertial subrange. We're not going to go into this theory. There's a lot of theory around that, very complex and very, very interesting. But I just want you to understand this basic concept. We're always taking energy from the big vortices, transferring it to smaller and smaller scales, and we're dissipating. Good. Let me finish up at the end. We'll just have a few examples explaining some applications, some turbulent, typical turbulent flows, just so you have them all seen at one point, and it will eventually lead over, or essentially lead over, to what we're going to do next week in the lecture on aerodynamics. So we have a bunch of turbulent flows, which we usually call free stream or free turbulent shear flows. These are flows like the turbulent jet you have seen in the beginning. And we have flows like a turbulent wake. We have also seen the beginning with the wake behind the cylinder. And we have turbulent shear layers. This is where a flow on top is faster than the flow on the bottom. We have a shear layer. These are all classical turbulent flows. But what I would actually like to show here, because this has some very direct practical applications, are wall-bounded turbulent flows. The wall-bounded turbulent flows are, for instance, the channel or pipe flows. You remember when we did exact solutions, we came up with this parabolic profile. That's the flow. You can see here on the dashed line on the left-hand side. Or you can have boundary layers like what you have on the right-hand side, which is, for instance, a Blasius boundary layer. Now, all of these flows can become turbulent by the process we have just discussed. And when we look at the mean component of these flows, so not at the fluctuations, just at the mean, we obtain the curves you see here as solid lines. There's something very characteristic about these mean turbulent flows. A turbulent boundary layer has a steeper velocity gradient at the wall than a laminar boundary layer. The turbulent pipe flow has a steeper velocity gradient, a sharper velocity gradient than a laminar pipe flow. What does this mean for the wall shear stress? We have learned that the shear stress at the wall is proportional to the gradient of the velocity profile. The steeper the velocity profile, the higher the velocity gradient, the higher the shear stress. So that means that on average, and for technical purposes, that's really what interests us, what is the average shear rate? On average, the shear rate at the wall of a turbulent flow will be higher than the shear rate of its laminar counterpart. This also means that the friction drag, or let's say the drag overall, will increase as soon as we have turbulent flow. This is the reason why most aerospace engineers, most engineers who design airfoils, want airfoils which have laminar flow on top of it. That's why they invest so much in keeping surfaces as smooth as possible to maintain them laminar as long as possible, because they want to reduce the gradient at the wall. They want to reduce the shear stress. And this is what is shown in these diagrams. We have looked at such diagrams a few times already. And this is what we looked at so far, the laminar line, the line here on the left. And it shows us what the drag coefficient here, this is a non-dimensional drag coefficient, what it is in function of the Reynolds number, right? We had here formulas like for the Blasius boundary layer and so on. At one point, this line moves away from this decay here, from this straight line, and moves over to a second line, which is the line for the turbulent shear layer. So we have an increase in the drag coefficient. So this point here is actually the critical Reynolds number. That's where the flow stops to be laminar. And over here, at this Reynolds number, that's where the flow has become fully turbulent. And in between the two, this is the transition region. This is where we do transition from laminar to turbulent flow. That's why it's not so easy to draw these lines, and these lines typically have somewhere a kink in it where you have usually transition from laminar to turbulent. And just as you have nice little formulas for drag coefficients for laminar flow, you have formulas for turbulent flows, for smooth plates, completely turbulent, different Reynolds number ranges, for transitional, mixed flows, and so on. These are all things you can look up in books, or better even use one of these tables. There's like a link to find some of these tables. Let me finish up today's lecture going back to the sphere or to the cylinder, because that's what we started with. So for very small Reynolds numbers, we have our Stokes flow, viscous dominated, no inertia. If we increase the Reynolds number, we start to get flow separation, which is a boundary layer phenomenon, and not yet automatically turbulence. There is a situation between Reynolds 4 and Reynolds 40 when you have flow separation, but you have still a laminar wake. Okay, so separation is not automatical turbulent. Very often it is, but it's not automatic. If you go a bit higher, you get these patterns here. Many people will call this turbulent, but you should know at the end of this lecture that this is not yet turbulence. This is still a highly structured, periodic flow. You have a periodic shedding of vortices, very regular periodicity, and the flow is highly structured, and you do not have a cascade of large and smaller and smaller and smaller and smaller scales. You just have a set of large scale vortices. This situation actually has a name. It's called the Kármán vortex tree, very well-known phenomenon. And only when you go to Reynolds number of 100,000 and so on, you obtain a turbulent wake, like what I drew on the black. And you have a turbulent wake if you go even higher up with the Reynolds number, like Reynolds beyond 300,000. The only thing that changed between this and this picture is that the boundary layer here transitioned from laminar to a turbulent boundary. Okay. And we'll look into this next week. This will be one of the main topics of next week, to understand why changing from a laminar to a turbulent boundary layer, why this makes the wake smaller. Look, the wake here is that thick, and here the wake is much, much bigger. Why this actually leads to a temporary reduction of overall drag. This is shown here on my last slide. You come here with the drag coefficient for the sphere. You have the Stokes drag, 24 over Reynolds. We go on. We're probably here, somewhere in the range where we have the Kármán vortex street. And probably here, we start to have turbulent flow. Turbulent flow with, or turbulent wake with a laminar boundary layer. And at this point where we have this dip, we actually do have turbulent boundary layer and turbulent wake. And why the drag coefficient goes down is counterintuitive, but we'll talk about this next week. This is called the drag crisis of a sphere. With that, I think we close here, and I would like to hand over to Kai, and we'll all see each other again next week when we continue with this slide to talk about aerodynamics, how to understand drag and lift of objects in an airflow. Okay, thank you.
Okay, thank you, Dominic. Into the class, let's take a 5-minute break and start again at 16.